Hi there, young scientist. Welcome to Labster. Today you will learn how our understanding of the atom has evolved up until today. You will study our current model of the atom and use it to identify the composition of a star in a galaxy far, far away. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer, such as music, sound effect, and voice. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect, then let's get started with your first mission. Find a lab coat and pick it up. Look at you, all suited up and ready to go. Great. Okay then, let's set off on our journey. Isn't it weird to think that your brain is made up of atoms and that those atoms are now going to learn more about other atoms? I'm made of atoms, too, mostly iron and carbon. Unraveling the atomic model has required the contribution of numerous scientists, building upon each other's ideas. Let's have a look at a timeline that explores the history of the atom. Alright, click on the wall screen to activate it. Go for it. The story of the atom begins more than 2,000 years ago in ancient Greece. Democritus was a Greek philosopher and one of the first to propose that all matter was made of tiny indivisible particles called atoms. Moving on, click on John Dalton. Democritus' concept of the atom was largely forgotten until John Dalton reintroduced a modern atomic theory into chemistry no more than 200 years ago. This marks the beginning of modern atomic history. Next up, click on J.J. Thomson. J.J. Thomson discovered the first subatomic particle, the electron, 120 years ago. Based on this discovery, he proposed a new atomic model known as the plum pudding model, where the negatively charged electrons were embedded in the positively charged nucleus of the atom. Who is next? Looks like Mr. Rutherford. Click on him. One of J.J. Thomson's students, Ernest Rutherford, then discovered the proton in 1917. From his experiments, he understood that atoms have a small, heavy nucleus with a positive electrical charge made of protons and that electrons orbit that nucleus, just like the Earth orbits the Sun. Bohr, that sounds familiar. Click on him to learn more. Niels Bohr improved the Rutherford model by adding concepts of quantum theory. He proposed that electrons could not have just any orbit they wanted, but, instead, that there existed only a set of discrete orbits with different energy levels that electrons could occupy, and that electrons must emit or absorb energy in packets called photons to jump from one orbit to another. In Bohr's atomic model, what happens to an atom if one of its electrons absorbs energy from an external source? Yeah, if external energy is applied to the electron, the extra energy will cause it to jump to an orbit further away from the nucleus. This atom now has high potential energy and is said to be in its excited state. Click on the View Image button to have a closer look. Since then, scientists have improved the atomic model in many ways. For example, in 1932 James Chadwick discovered that the nucleus wasn't made only of positively charged protons, but also of another subatomic particle without any electrical charge called the neutron. What are the three subatomic particles found in an atom? Correct. We might take this for granted today, but the subatomic particles were all discovered within the last 130 years. You already know secrets that were previously unknown to many great scientists. Right, let's move on. Last one. Click on Schrödinger to find out what he was all about. All these improvements were incorporated into the latest version of the atomic model, the quantum mechanical model or Schrödinger model. Erwin Schrödinger discovered that electrons are not actually particles, but rather quantum mechanical particle waves. In Schrödinger's model, electrons do not orbit the nucleus and they don't have set positions or paths. Instead, each electron has a wave function, like a probability cloud that tells the likelihood of finding that electron in a given region of space. When an electron is inside an atom, its wave function is called an orbital. Good job! We still have a lot to learn about the atom. Maybe one day, you'll be part of this timeline. But right now, let's go into the main lab room and say hi to Dr. Nova. Enter the lab.
Hi there, it's very exciting to meet you. Allow me to introduce myself. I'm Dr. Nova, renowned Labsterian Aeronautics and Space Administration astrophysicist. Some people say I have the same fashion sense as Albert Einstein, but rest assured, I'm not him. I have a marvelous mission for you today, but I still need some time to download the data we need. While I prepare our big mission, I would like to invite you to review some holographic models I created for educational purposes. Please take a look at Bohr's planetary model and Schrödinger's quantum mechanical model.
Good old Dr. Nova, I really love that guy. Click on the workbench on your right to review his atomic models. Click on the hollow table to your left to activate it. Bohr's model of the atom is accurate enough to visualize many atomic processes. Still, it has important limitations. Bohr's model could only explain the energy levels of the hydrogen atom, not of any other element. It could not explain that most energy levels have sub-levels, and it contradicted the uncertainty principle, which states that particles can have well-defined positions and well-defined velocities at the same time. These limitations led to the development of the more accurate quantum mechanical Schrödinger's model. What were some limitations of Bohr's atomic model? Congratulations! Bohr's model is intuitive, and it was the first atomic model that incorporated quantum concepts like discrete energy levels. Yet, Bohr's model had important limitations, so it was replaced by the Schrödinger model. Schrödinger's model is compatible with quantum mechanics, can explain energy sublevels, and correctly predicts the energy levels of atoms of any element. Click on the hollow table to your right to activate it. In Schrödinger's quantum mechanical model, electrons do not have orbits. Instead, they have associated orbitals, probability clouds that describe the likelihood of finding an electron in a certain position. The denser the cloud is somewhere, the more likely it is to find the electron there. Schrödinger's orbitals are defined by a set of 4 quantum numbers, which serve as coordinates. These 4 numbers identify the exact energy level and sublevel of an electron in the atom. Let us have a quick look at the 4 quantum numbers. Click all the Show Image buttons on the display to your right to learn more about the quantum numbers. The principal quantum number tells us the size and main energy level of the orbital. In Bohr's model, it also corresponds to the size of the electron's orbit. Bigger orbits have higher energy levels. The angular quantum number describes the shape of an orbital and its energy sublevel. The magnetic quantum number describes the spatial orientation of electron orbitals. The spin quantum number is a bit of an oddball. The word spin is misleading. Remember that we are dealing with the strange nature of wave particles, so electrons can't actually spin. The spin number refers to certain magnetic properties, rather than the actual rotation of the electron. The spin number is important because only electrons with opposite spin can share an orbital. Well, now that you have identified an electron and its orbitals, let's see if I could make a successful analogy with a traveler. Remember to activate your imagination. Click all the analogy buttons to view the analogy. The traveler may walk on shorter or longer paths depending on how much energy they have. The principal quantum number is also determined by the energy and size of the electron orbital. The path may have different shapes, and the shape might slightly influence the energy needed to walk the path. The angular quantum number depends on the shape of the orbital and influences its energy. The traveler may take a path with a different orientation, south to north or west to east. The magnetic quantum number is related to the orientation of the orbital in a similar way. The traveler may walk with someone, but the other person must be upside down. Kind of like how only electrons with opposite spin can share an orbital. How many types of quantum numbers are there? Correct. There are 4 quantum numbers: principal, angular, magnetic, and spin. What quantum number determines the energy and size of an orbital? That is right. The principal quantum number determines the main energy level of the electron and describes its most probable distance from the nucleus. The larger the number n is, the more energy the electron has and the further it is from the nucleus. What are electrons in Schrödinger's quantum mechanical model? Indeed, Schrödinger's model is quantum mechanical. This means that it describes both the particle-like and the wave-like properties of electrons. You might be wondering what all this talk of atomic models, electrons, and orbitals has to do with identifying the atoms a star is made of. So, let's crack on and find out. Click on the hollow table next to Dr. Nova to examine an atom in the gas cloud. Okay, first off, let's load this bad boy up. Pick up the electron from the hollow table and place it so the atom is in its ground state, the lowest energy level and the closest to the nucleus. Pick up the electron from the hollow table and place it in the correct orbital, to set the atom in its ground state.
Great, so the atom is now in its ground state. Now, photons of many wavelengths are bombarding the atom. Can you figure out how the atom can absorb some of the energy from the light?
Help the atom absorb the energy from the light. Click here if you need help.
That is clever. When the electron absorbs energy from the photons, it jumps to a higher orbital and becomes excited. The energy levels of different atoms are all different, so each element absorbs a distinct set of photons of different energies and wavelengths. Now, can you figure out how the atom releases all that energy it has just absorbed?
Help the atom release its energy by picking up the electron and placing it back on the inner orbital. Make sure you slide your lab pad down so you don't miss any of the action.
Did you catch that? It happened at the speed of light. This is how an atom emits energy.
Can you think of where the concept of absorption and emission might be applied to bringing some color into your life? Exactly. When fireworks explode, gases are created with electrons jumping from ground state to excited state and back again. In the process, the energy released appears to us as bright colorful explosions in the sky. The colors we see depend on the chemicals in the fireworks. If we want a blue explosion, we use copper; for a green one, we use barium. And so on. Click on the big wall screen next to Dr. Nova to go there.
Okay, let's get down to business. Last year I sent a space telescope into the Earth's orbit to capture the starlight of a previously unexplored galaxy. We can learn a lot about the atomic composition of a star by analyzing its light. It's rather amazing, isn't it? I installed a detector in my space telescope to record and measure the light from the stars. This device uses a glass prism to split the different wavelengths of white light so that we can study the color spectrum. Click on the View Image button to have a closer look. Righty-ho. Now, please select a star that you'd like to analyze.
Click on the star you would like to explore.
That's a beautiful star. Okay, let's have a look at the starlight's incredible journey all the way from the star to my space telescope.
Click on the light source.
Imagine that the star had no atmosphere. Stars emit photons at every wavelength, so when their light travels directly to the space telescope, it is recorded as a continuous spectrum. It looks like a rainbow, with light of every color.
Click on the light source again, to find out what effect a cold gas cloud has on the light. There are some black lines in the absorption spectrum. Can you figure out what these are? Exactly. This is known as the absorption spectrum. The black lines in the spectrum are the wavelengths of light that were absorbed by the electrons in the gas cloud. Electrons can only absorb some of the photons, those with the exact wavelength that gives them the energy to jump to a higher energy level. The energy levels of different atoms are all different, so each atom has a unique set of photons it can absorb, and therefore a unique absorption spectrum. Click on the View Image button to have a closer look. The image below displays the absorption spectrum for hydrogen and the corresponding jumps between electron orbits. Based on what you can observe, what wavelengths does hydrogen absorb? Click on the View Image button for a closer look. You are right again. These four colors are missing from the spectrum, so they must have been absorbed by the hydrogen atom. These colors correspond to the wavelength of the photons an electron of the hydrogen atom can absorb to jump to a higher energy level. Click on the gas cloud to release the energy. Look at the image on the wall screen or click on the View Image button. What is the connection between the absorption and emission spectra? That's right. Emission and absorption spectra are complementary. The lines missing in the absorption spectrum are the only lines in the emission spectrum. That is because the photons an electron can absorb to jump to a higher energy level are also the photons it can emit to jump from that higher level back to the lower level.
As you so brilliantly deduced, the same wavelengths that were previously absorbed into the gas cloud are now released when the electrons jump closer to the nucleus. These wavelengths are then captured by the space telescope, and we see them as the emission spectrum. Click on the View Image button to have a closer look. A star produces light in photons of every wavelength. However, the atoms of its atmosphere can absorb photons of the specific wavelengths that their electrons need to jump from one energy level to another. Therefore, each star has its unique absorption spectrum based on the atoms in its atmosphere. And now for the grand finale. Will you be able to figure out what elements the star is composed of?
On the table in front of you, there are 3 cards. Each card has the absorption spectrum of a different atom. Match the cards on the table to the spectrum of the star to find what atoms are there in the atmosphere of the star you picked. Pick up a card. Place the card on the screen. Notice that the spectrum labeled, "Your Sample," at the bottom of the screen, has been updated to reflect the card you chose. Click that Submit button when you have matched your spectrum to that of the star. Well done! The spectrum of the star matches the spectrum of the hydrogen atom, so the atmosphere of the star must be made of hydrogen. We've been lucky this time because there was only one type of atom in the star's atmosphere. However, most stars contain more than one type of atom. In that case, the lines of all the atoms in the star show up in its spectrum, sometimes even overlapping.
This next star has atoms of 3 different elements in its atmosphere. Ready to figure out the composition of a more complex star?
Figure out what elements are needed to recreate the star absorption spectrum. Congratulations, you made it. Great! What 3 elements are in the atmosphere of the star? Congratulations! The lines missing from the star's spectra are the lines of the absorption spectra of hydrogen, sodium, and magnesium. So the star's atmosphere must be made of atoms of hydrogen, sodium, and magnesium. You deduced the composition of the star in a galaxy far, far away. Amazing! Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.